we're having two guest lectures today. This is our big guest lecture day. And we have TFs, and we have Tianxiao is one of our TFs, and we have a guest lecture from Manolis Kellis at MIT. So maybe I'll let Tianxiao begin.
Okay, thanks, Mark. So yeah, I think we're having enough people. I think we're having enough number of people. So my name is Tianxiao. I'm your TA for the class, and today I'm going to give you a brief introduction about text mining in biological and biomedical literature. So I'm going to first give a brief introduction about the text mining and natural language processing problems and tasks in biomedical literature in general. And then I'm going to specifically introduce some of the deep learning methods that are applied to these tasks. So let's first talk about biological literature. And before that, I think we first need to raise the concept of structured and unstructured data. So for example, if any of you have ever used databases like StringDB, which is a database for protein-protein interaction, you have those very fine structured tables that indicating like both of the proteins that are interacting, and you have their accession ID that you can query, and also they provide you with a score of confidence of that interaction. So this is the structured data that you can typically directly use to your analysis when, for example, when you're trying to build a regulatory network or protein-protein interaction network, you can directly make use of those structured data. But in reality, most of the information in biological literature, they do not come in this perfectly structured way. Most of them exist in those kind of free text or unstructured data. And for example, if you want to know anything like BRCA1, you need to go through the literature, go through the text, and try to figure out with your human brain whether a certain sentence that contains that specific protein is implying an interaction or not. And so this is what we would like the machine to do, because we cannot let a human being to go through all the literature and then figure out all those interactions by hand, and that will be very costly and inefficient. So we want a machine to be able to extract this kind of information by themselves. And so specifically, if you look at StringDB, they actually have one kind of edge called text mining. That is the information they obtain from pure text mining. That they just like coexistence of such of the two proteins in the same paragraph or the same sentence. And although we don't typically consider that alone as a good indication of a interaction, we sometimes use as an auxiliary information for analysis. And if you look further into that, they actually provide you with pieces of text where that information is mined from. So this is like one clue, one piece of information they have, one piece of text from which they obtain that interaction. And you can see they figured out, they labeled all of those protein names or gene names in a paragraph, and they also assign them to different categories and different entities. That is to say, like, for example, if you look at it, there are a lot of interesting things you can look at. For example, there's a problem of multiple different names for the same gene or protein. You have FANCD1 quote BRCA2. That's actually referring to the same thing. And also, you have like this partner and localizer of BRCA1, which in short, in abbreviation, is PALB2. And they are also referring to the same thing. So if you're doing the most naive method of like looking for the gene names or protein names from a set of predefined names, you might consider this, you might regard this as a mention of BRCA2, which is not, which is actually a mention of PALB2. So this is one natural language processing problem we encounter when we are doing this kind of analysis. And I'm going to talk about this later. So this is called named entity recognition. And we can have also many other examples where we have tools that can identify those different mentions of biological entities. And not only that, we can also assign them to specific categories. And here I have listed out basically most of the natural language processing tasks we have when we are analyzing biomedical literature. First of all, that is named entity recognition. That is like identifying the mentions of specific entities in the text. This includes like the data is structured like this. You have like a sequence or a sentence, and where you have labels, different kinds of labels indicating whether it is a mention of entity or is not, and what kind of entity is that. And it also defines the boundary of the entities, because you sometimes have a whole phrase referring to one thing. This is the named entity recognition. And when we are trying to extract information like protein-protein interaction, we want to extract the relations from the text. And this is usually done after you do the named entity recognition. That is to say that you can extract sentences where you have identified, like, say, for example, you're looking for the relations between genes and diseases in this example, and then you first do named entity recognition, and you pick out the sentences that contains a gene and a disease, and you replace them with the wildcards of genes and diseases, and you're trying to figure out whether that sentence implies a relation or not. So the idea here is that whatever gene or disease you place here, if the sentence is structured this way, that infers relationships. So whatever gene disease that is like a universal rule that you can apply to every single piece of text, and that is what you want to learn. And also, again, finally, we have question answering. That is, you have two sentences. Actually, so the data set is formulated as this. So you have two sentences or a sentence and a phrase, and they are labeled positive if that is a valid answer to the question. And then you're trying to learn a machine that can help you find the answers to those questions. So these are the three important tasks that are usually important in the study of biomedical literature. And next, I'm going to briefly talk about clinical records. So there were data sets like MIMIC, which is abbreviation for Medical Information Mart for Intensive Care. And this is a database that is used very widely in mining of electronic health records. And it is a massive database that contains all kinds of information, like including like those monitoring signals and charts, and most importantly, notes and reports. This includes like discharge summaries and radiology and cardiology reports. And this is kind of the kind of text we are mining when we are analyzing electronic health records. And of course, sometimes we get this also, we do this analysis also including some of the other auxiliary information from other sources of data. So this is an example of what this looks like. So you have a piece of free text that is the discharge summary that is written by a clinician. And you have those hand-curated labels. Those are curated with the standard of like called ICD-9. That is an ontology for diagnosis. That is like all this kind of diagnosis you have from this piece of text. And you want to do a class, you would want to mine this kind of information from this piece of text if you provide it with a new piece of discharge summary, for example. And this is basically a classification task. Then you're trying to assign this piece of discharge summary to those diagnosis classes. So yeah, in summary, these are the 4 kinds of tasks that I mentioned, the 3 that I've mentioned before. And also we have the problem of classification that is similar to every supervised classification you have learned so far. Yeah, so that's all about the tasks and problems we have for biomedical literature. And next, I'm going to specifically look at some of the deep learning methods that are implemented for these tasks. And yeah, before the advent of deep learning, many of them are done using like some like rule-based method and a semantic and syntactic analysis that requires a lot of linguistic knowledge. And I'm not going to talk about that in detail. I'm just directly going into some of the recent deep learning methods for these problems. So one of the typical, and I think one of the very straightforward methods you can come up with when analyzing text is a recurrent neural network, because this neural network architecture is designed specifically for the analysis of sequences. And you assume that each element in the sequence has some dependencies on the elements preceding it that is perfect for modeling of language. And you have the architecture of recurrent neural network, and I think we have already covered some of this in class, where you have the same computational units repeating itself, and every time it's feeding its hidden layer output to the next position in your sequence as part of the input, and you do this in a recurrent way. And we know that there's a problem with the vanilla or the simplest recurrent neural network architecture because you have the problem of vanishing or exploding gradients. That is to say, because you are repeating the same computational units multiple times, if you're having a very long sequence, when you are calculating the gradients, you are multiplying the derivative term for the specific weight for the same set of weight a lot of times. And if that value is greater than 1, it gets exploded in an exponential way. And if it's smaller than 1, it vanishes. So to address this problem, people designed this architecture called latent long short-term memory, LSTM. That is, besides, so different from the simple computational units, they actually added 3 gates. They're called input, forget, and output, and that determines how much information you pass on, you receive from your previous computational units, and how much information you pass on to your next hidden units or to the output. So these 3 gates have their own weights that are learned from the input, and they determine how much information you carry over. So this is how RNN or LSTM is usually used in a task like translation, where you are inputting. This is called a sequence-to-sequence model, and that's mainly used for translation. And you can try and kind of input your a sentence from your source language combined with your sentence from the target language, and then you're trying to predict the words in your target language based on whatever you have seen so far. But translation is not usually a big problem when we are looking at biomedical literature, but we can also do classification using recurrent neural network. For example, if you want to have a classification over the entire piece of text, as in the ICD labeling, you can build your classifier on top of the last output of the sequence to predict like specific targets, whatever targets is in your task. And also, of course, you can also do classification on every single element, every single position in your inputs. For example, for name identity recognition, you can build a classifier on each one of those outputs, indicating whether it is a named entity or what kind of named entity is that. So this is the application of recurrent neural networks. And of course, you can also consider the text as an image. And in that case, you can apply the convolutional neural network. So you are kind of treating the sentence as a 1D image, and you're applying 1D convolutional kernels onto it. And then you can do the same thing as you do with every convolutional neural network. You can max pool those convolutional features, and then build a classifier at the end of the model. So so in order to accommodate your input sentence to the convolutional input, you need an embedding vector for each of the words in your sentence. That is, as a result, you're having a matrix input quote image with size of D, with size of the length of your sentence, and when the number of the rows or the number of the features are the dimension of your embedding vector. And you can do this, and then you can do your convolutional computation and your classification on that. And so next, I'm going to talk about how that embedding is usually done. So this is the problem of word embedding. So a typical and straightforward way to do this is, as we have seen in this example, is the one-hot encoding. That is, for example, if you're having n dimension, you're having a vocabulary of size n, that can be specific words or also subwords. Or if you're looking at specific terminologies, you can have like each concept as a word, as is the case here. So here, you are actually encoding those clinical concepts rather than independent words. And whatever you define that, if you have a vocabulary of size n, you are embedding each of the input, each of the words in your vocabulary as a vector with n dimensions. And most of the values are 0, and each of the dimensions correspond to a specific word in your vocabulary. So whenever that word exists, you are putting a 1 into the corresponding dimension, and all the rest are 0. So of course, there are several limitations of this kind of embedding, because first of all, it's not very computationally efficient. You're having an n-dimensional vector, and most of them do not carry any information. Only one of the dimensions are informative. That is one thing. The other thing is you cannot compare the terms or the words with this kind of encoding. You cannot evaluate their similarities or their relations because all of these n dimensions, they are orthogonal to each other and they are exactly the same. So that's only indicates the existence of that word without carrying any information about the word itself. So because of this, people develop methods like of embedding methods that compresses this n-dimensional one-hot encoding vector into a lower dimensional continuous vector. In that case, every single dimension carries some information. And also, those embedding methods are learned so that the vectors store information about the relations or the contextual dependencies of these words. So you can directly compare the embedding vectors of two of the words, and that will give you an idea of whether they are related or whether they are similar. So this is the idea of embedding. And one of the methods to do this is called GLOVE, which is short for global vectors. Yeah, I think people are asking questions. I think I can take the question later. So yeah, I'm going to directly answer that here. So the GLOVE, which is not actually a deep learning method, which is actually a matrix factorization method, but that gives you an idea of how that is done. So for GLOVE, you're providing the model with a co-occurrence matrix or a context matrix that indicates the frequency of each word coexisting with each other. And then you're trying to do a matrix factorization and then decompose this co-occurrence matrix into the product of a embedding matrix with the transpose of itself because it's symmetric. And each of the rows here corresponds to a single word. And you can take that vector as your embedding vector because that contains information about your contextual preferences of the words. And you can then somehow reconstruct this co-occurrence matrix by simply comparing the embedding vectors in this embedding matrix. And then came the concept called word-to-vec. So this is the idea of word-to-vec is that you can learn about the word by looking at its context specifically. So they design a model that tries to predict the words based on its context or predict the context based on the words. So the input of the model is kind of like a sliding window that you walk through all the sentences in your input text. And for every single word, you are extracting like a context of fixed size before and after it. And each of them makes up a input vector. And the same thing for biomedical literature. When you're focusing on a certain word, you extract its context as your input to this model. So there are actually two constructs of the model, one called continuous bag of words, the other called skipgram. And for SIBO, you are trying to predict the word based on the context. And for skipgram, you're trying to predict the context based on the words. So both of them can work. And how they work specifically is that after you train the model, so you already have a model that either learns the context, either predicts the context from the word or predicts the word from the context. And then you can directly look at the model weight. That is the weight you apply to your input vector. And that is actually your embedding vector because it has a dimension that is the same as your, it has a dimension that is the size of your vocabulary times the dimension of your embedding. So this matrix is your embedding matrix. And then you can use that to do any analysis for word embedding that requires word embedding. And people have also developed a method that utilizes recurrent neural network called ELMO. So the idea is very similar. But here they're trying to predict every next word based on what you have already seen. So the ELMO is basically a multi-layer LSTM. And for the training, you are trying to predict every word based on what you have already seen so far. So that is how this works. And in actuality, they are actually implementing two recurrent neural network, one forward and one backward model, one forward model and one backward model. So you can train this model that tries to predict the word, again, by its context. And after this is done, you have the model that contains the information about the embedding. So you can then extract the hidden representations of every input word and concatenate them and then aggregate them to get your word embedding. And then you can directly use that for your classification tasks. And also we have the model called BERT. And BERT is actually, so before that, there was a model called transformer. That is a sequence-to-sequence model that does translation, where you first have an encoder that transforms your sentence from the source language into a lower dimensional continuous embedding space, and then you're decoding it to your target language. So BERT only utilizes the encoder. So what it does is that you have an input embedding vector for each of the words in your sentence, and then you're first feeding into a self-attention layer. I'm going to explain this later. And that gives you a contextualized representation of each of your inputs, each word in your input. And then you have a feed-forward neural network to aggregate that information and feed that to the next layer. So this is how the attention is calculated. And it's like you can consider that as in a traditional neural network model, you only have a weight that is applied to your input vector and transforms it into some like value representation that you can pass on to the next layer. So this is the same thing as the value matrix in BERT. And but the difference here is that with an attention mechanism, they are calculating two more matrices, one called key and one called query. And from that, you're calculating an attention, which actually, if you interpret this from a natural language processing perspective, the attention matrix is one that captures the dependencies between the words. So for example, if you have an input sequence with length L, you are calculating a attention matrix with L times L dimensions, and each of the elements corresponds to how every word in your input attaches weight to every other word in the input. Because as you can imagine, a language, the meaning or the function of the word is implied by its context, but not all of its context. Some of the contexts are more informative, some of them are not. So that's why they are defining this attention matrix that tries to capture this kind of patterns. And when you're calculating that, they are actually calculating two matrices. They have their own weights. They have their own model weights that can be learned. They're called query. And then that gives you the values of the queries and the keys. So you can consider that as you're trying to use a query vector to scan through the entire sequence and match it with every single key in your input. And then you're attaching higher weights to the positions or to the words that gives you a better match. That is why they're doing a softmax here. So you're going to attach higher importance to the words in your input that are more informative or more related. So this is what it basically does. So they actually have 8 attention heads in the BERT model. And so you can consider them as the convolutional kernels in a convolutional neural network, where each of them captures some certain kinds of dependencies. And you have those 8 convolutional kernels. Each of them gives you a query, key, and value outputs of its own. And then you calculate the attention and aggregate the values into a lower dimensional vector representation called Z. And you have 8 embedding vectors. You have 8 attention heads. You are concatenating the output of all those 8 attention heads, and then feed it to a feed-forward neural network that gives you an output of the same size as your input, same dimension as your input. And then you can feed it directly to your next layer. So this is how the model, the basic computational unit looks like in the BERT model. And for training the model, they are using the same concept of predicting the word from its context. They are providing a model with masked languages. That is, they have sequences with randomly masked tokens that are replaced with like a null token. And then you're trying to predict those masked words based on the context. So after you train the model learns a lot about the dependencies between those words. And they are actually training this on perhaps the largest English corpus you can find on internet. That is the most of the Wikipedia articles. And they also use some other sources of input data. But as a result, you have a model that already learns from a very large English corpus about the basic dependencies and the grammatical rules between those words. And then you can apply this to maybe smaller tasks like question answering or name identity recognition, something like whatever you like. You can initialize your model with those pre-trained weights that you transfer the information, transfer the knowledge you have already learned from a much larger corpus to your very specific domain. Because many of the rules and grammars in the English language are universal, whatever corpus you're looking at, right? And then you're building your classifier on top of the output, which is the embedding of the input sequence. You can build a classifier on top of your outputs. And then that classifier does the same thing, that does the task-specific prediction. And then you can train this model so that you can learn some of the task-specific dependencies while also utilizing the general universal grammatical rules that you do not need to learn again, relearn in this in your smaller task. For example, if you want to build a classification, you're building a classifier on top of the model output. So yeah, in practice, we're usually adding a class token at the beginning of the sentence, and we consider that as an aggregation of the entire sequence. So then you're building a classifier on top of the embedding of your class token that predicts, for example, whether the input is a spam or not. And the BERT model is trained on Wikipedia corpus, and also like there's another data set called book corpus. And they are more suited for like modeling of generic English languages. But we know like in biological literature, we have not only slightly different vocabulary or terminology, we also have maybe a different style of writing or different, kind of a slightly different logic of language. So people have also trained a model called BioBERT that is specifically tuned on not only the English corpus, the general English corpus, but also PubMed articles. So they are training this model on a more domain-specific corpus that is here PubMed text. And they claim that this will suit better for biomedical text mining and natural language processing. So this is what they're basically doing. That's the same architecture of BERT when they're also feeding in PubMed articles. And also here are the same tasks that I've shown you before. You can build your classifier that predicts those certain kinds of labels depending on how your training data is structured using your pre-trained BioBERT weights. And finally, I'm going to show you how this works. So how it works. So people have been comparing those different tasks using a generic English language BERT and the BioBERT. And they can see that, especially in the definition of the border of the name entity, for example, in a name entity recognition, when you train a model on a biological text, you're having a much better performance. Some of them, like in a generic BERT, you are not going to recognize some of them as named entities, but you can do that when you have a model trained in the biomedical corpus, with the biomedical corpus. And also it deals with some certain abbreviations better, because in a traditional BERT, they might just ignore it. And also the boundary of that named entity. So actually, like penicillin itself is already a named entity that you can, that is already, so penicillin here is the named entity you're looking at. Is not like a penicillin anaphylaxis. That is not a valid named entity if you're looking at biological literature. And also for question answering, they also find like they're a little better when looking for the boundaries of the concepts and terms, where when in the generic BERT, they're more kind of like identifying specific words, like individual words, treating them as independent words, while in actuality, they themselves constitute a named entity. So this is why like this pre-training would be a very good idea when you're doing domain-specific text mining, because that incorporates a lot of knowledge specific to your small domain. Yeah, so this is how BERT works, and that's basically what I have for today. And I don't know if you have any questions.